So this is a method for finding zeros of a function. So first, before we start, there's a couple. Okay. So Newton's method is a technique for approximating real number zeros of a function. So a zero would be where the graph of the function crosses the x-axis or where the y value of the function is 0. And we do so using a tangent line to approximate the graph near its intercepts. So here's the basic setup. Your function has to be continuous on some interval and differentiable on that interval. And on that interval, f of a and f of b are different signs. So this might be my a, this might be my b. Does that make sense? So on one side the function's negative, on one side the function's positive. So the first thing you do is you pick an initial guess and you call it x sub 1 that is close to your 0. To make sure that your answers are like consistent in WebAssign, they will sometimes tell you what to guess initially. And then you find the tangent line at x1. So that means your point is x1 comma f of x1. What's the slope of that line? How would you find the slope of the tangent line at x1? Derivative, and what would you plug in for x? x1. Okay. So that tangent line is going to be y minus y1 equals mx minus x1. So y minus f of x1 equals f prime of x1, x minus x1. Or solving for y, it's going to be y equals f prime of x1 times x minus x1 f prime of x1 plus f of x1. That was a lot of letters, but just moving stuff around. Okay, so in this picture, the thing you want to find is what they're calling this number r, the root or the 0 of the function. Look at this tangent line. x1 was our initial guess, which doesn't look very good. But if you look at where its tangent line crosses the x-axis, does it make sense that x2 is closer to that root? So what is x2 to this line? Like, it's a very special point on the line. It's the blank intercept. Fill in the blank. It's the X intercept. So your next guess is the X intercept of the tan line. And how do you find that? How do you find an X intercept of something? What do you set y to 0? So take this equation we just found, set y to 0. So 0 equals f prime of x1 times x minus x1 f prime of x1 plus f of x1. Solve for x. And I mean x, like I don't mean solve for x1, I mean solve for x, get x by itself. So how would you start doing that? Which terms don't have x in them?
The last two?
The last two don't have x in them, right? So I'm going to put this term and this term on the other side. So I'll have x f prime of x1 minus f of x1 equals f prime of x1 times x. And now how would I find x? Divide the whole thing by f prime of x1. And that's going to give me x equals, well, that should be an x1 over here, shouldn't it? x will equal x1 minus f of x1 over f prime of x1. And we call this thing x2. x2 is our next guess, as in our estimation of what that 0 is. And look at x2 has gotten closer to that r number, hasn't it?
So we just keep doing
And
this
this
over and over again?
picture is saying, then repeat the process. x2 is next guess, repeat with x2. And you're gonna follow the exact same process. It's just all the number ones change to twos. And then you solve it. And your next guess, x3, is gonna be x2 minus f of x2 over f prime of x2. And that's gonna give you this tangent line. It's gonna find you that point. Does that make sense? And you do it again. And this next tangent line will find you that x4. And eventually, as long as you choose well and some conditions are met, these numbers that you're gonna find when you repeat this process are going to get closer and closer and closer together until they're almost indistinguishable.
How do you know if you go too far?
It'll be really obvious because you're gonna start getting the exact same answer.
Oh.
So when you start to do this repeatedly, you're gonna get the exact same answer. But the point is you have to use the answer from your previous step to do your next step. So when you have to use a calculator for this, and to do so, you have to also make sure you're not rounding your answers midway through, that you use the whole answer. Calculators have those like ANS features where you can use the answer as opposed to having like retype the thing in. If you don't know how to use it, I'll show you, okay? Okay, so here's the general step. So, let's see if I have them typed. So the first thing is you make an initial guess, x1, that's close to your c. Sometimes you might want to like actually graph the function and like look at where the graph crosses the x-axis and say, okay, this number's pretty close. This is the formula for your new approximation. And think about before we had like x3 equaled x2 minus f of x2 over f prime of x2, right? The point is the new approximation as an n plus 1, one more than the old one. And then if the difference between two successive approximations is within desired accuracy, you let that last approximation serve as what you're going to use. Otherwise, you just keep going. And so the difference being like within desired accuracy just means you're going to get answers that have like a bunch of matching decimals. Okay, so let's actually look at something with specific numbers. Okay. So we're going to calculate 3 iterations of Newton's method to approximate a 0 of this function. And we're going to use x equals 2 as our initial guess. Okay, so the formula is xn plus 1 is xn minus f of xn over f prime of xn. So we're going to need to use both f and f prime. So how about you go ahead and just tell me what f prime is?
X squared minus 2.
Okay. So our x1 is equal to 2. I think that officially counts as the first iteration. x2 will equal x1 minus f of x1 over f prime of x1. Okay, so that will equal, what goes in for x1? 2. Minus f of 2 over f prime of 2, right? So that'll be 2 minus 2 cubed minus 2 times 2 minus 5 divided by 3 times 2 squared minus 2. Do that and see if you can get the same answer as me. It should be a nice answer, actually.
Negative 110.
Definitely didn't get that. I got 2.1. Did you put parentheses exactly where I put them? I got 2.1. Since Rachel also got 2.1, I feel like I'm probably correct. Okay, and then how would you find x3? x3 would equal what?
2.1
Yeah, I'm going to say it like this first. x2 minus f of x2 over f prime of x2, but I think you were there. So it will equal 2.1 minus plug in 2.1 into f divided by plug 2.1 into f prime, right? Okay, so go ahead and try that. One cubed minus 2 times 2. Did you find your mistake yet?
No.
Oh, it's the same. She just.
What she did in parentheses, the division, that's the negative 110. You have to subtract that from 2.
Yeah, I got 1.9.
Oh, okay.
Oh, did you not do 2 minus that? That's it.
Okay.
Because that would do 2 plus 0.1, and that would give you...
Yeah.
Okay, there you go. So I got this one was approximately 2.0946. Okay, because this one, let's do x4 just because I want to see if you can use your calculators right. So x4 will equal x3 minus f of x3 over f prime of x3. Yeah, so get it out and try. They're all going to be slightly different. So what people that have TI 80 whatevers, those I'm pretty sure I know how to do, but the ones that are not TIs, I'm not as familiar with. You should have some kind of, so what you need to do first with your TI whatever calculator is punch this thing in and get an exact answer. Do you know how to make your calculator always do decimals? Because I can show you that.
Well, basically what I do is if I want to know what 3/2 is in decimal, I put a decimal point after it and it gives me it in decimals.
Okay, so you can do that. There's a way to change the formatting so it always goes decimals though as well, or vice versa. But, okay, so did you get that? You know, a calculator? Damn it. Okay. All right, never mind then, we'll skip that x4. But the point is there's a little thing that says ANS in most calculators, and that uses the previous answer that you had. So you can type this in as ANS minus ANS to the third minus 2 times ANS minus 5 divided by 3 ANS squared minus 2. And that will actually let you just repeatedly just type in that exact same thing again and again. It'll make the calculation go kind of quickly. So just use that feature because it will carry along all the digits. Otherwise, you're going to have introduced rounding accuracy that's going to be lost. Okay. So use Newton's methods to approximate the zeros of f of x equals e to the x plus x. Okay, so when I graph this thing, what do you get when you plug 0 into this function? 1. No, when you plug 0 in, you get 1, if you're right the first time. When you plug in positive numbers, you're going to get positive things, right? When you plug in negative numbers, like say -1, f of -1, that's going to be e to the -1 minus 1, or 1 over e minus 1. And 1 over e is kind of like a half, right? Because it's 1 over 2 more like a third. It's going to be a negative number of some sorts. When you plug in -1, you get a negative number. So the negative happens someplace in between -1 and 0. There's a 0 in that place. So you're going to do this process until you get 2 successive iterations that differ by less than that much. So the closer you pick your first guess to the actual 0, the less iterations you have to do. So when I did this, I graphed it and looked at about where it crossed, and I used as my first guess x1 equals -0.6.
still do, when it's not like distance from.
No, you're not using the distance formula, you're just figuring out where is this crossing point, not the distance between 2 points. And what is the derivative you're gonna use in this process? What's the derivative of this function? Yeah. Don't let me down, guys. So x2 will be x1 minus f of x1 over f prime of x1. Let's just write down what that will look like and I'll tell you what I got. So it should look like that. And I got about negative 0.56695. Did you get that too? It's okay if you're still punching.
Yeah.
Yeah, okay. So then how would you find x3? You'd plug in x2 minus f of x2 over f prime of x2. I should just tell you what I got for that. I got negative 0.56714. And comparing x2 and x3, how many of the digits match now? 2. Okay. And we need 1, 2, 3, 4 of them to match, and the fifth one to be less than 0.1 away. So, but here's kind of crazy. x4, when you find that, you also get negative 0.56714.
Oh, that's the repeating part.
And that's the whole part where you're seeing you're going to get something that ends up looking almost the exact same. Some of your calculators have a feature where they solve something for you and get you a decimal approximation of it. They might be using this method. Because they're like, okay, now I have 10 decimal places matching. This is good enough. This is where the 0 is. It's within whatever accuracy I need. So my friend who's an electrical engineer he says they use this kind of thing all the time. Well, in calculators, but they have to know how this stuff works in case it isn't working correctly. He knows so much math. You can't be I don't think you can be an effective engineer and just only be a button puncher. Yeah. So. But yeah, that's. Mm-hmm.
Would it matter which x4 you're going with?
Well, the one that you give is the one where the matching happened. Does that make sense? So you just stop with the one that when that one happened is when there was enough matching going on. But I think the answer you give WebAssign is the matching digits. So it wouldn't really matter if you gave it x3 or x4 because they're the same. But you have to find x4 to know that they matched. Okay. So you can also use it, instead of just finding zeros, you can use this method to figure out where functions intersect. Because you can translate a question about where do two things intersect into where's a zero of a related function. So if two things intersect, then what's true about them? If two graphs intersect, so graph and, let's actually draw the graphs for real. So you have the ln graph, right? We have the y equals negative x graph, right? Approximately. If they intersect, their y values are equal, right? So we're going to find our points of intersection, when f of x equals g of x, right? Or when negative x equals natural log of x, right? Or same thing as saying 0 equals natural log of x plus x, isn't it? So a question of intersection points can be made into a question of where are two things equal to each other, which can then be translated into, okay, well, where do these two things, when they're added or subtracted, equal 0? Right, depends on the addition, subtraction, depends on what the original equation looked like in the first place, right? So you define a new function, I'm gonna call it h because that letter hasn't been used yet. H will be ln of x plus x. You can't call it f or g because f and g are already used. I guess in math you can't have two people with the same name. It's just too confusing, just like it is in life.
No homonyms?
No, things are just, yeah, no homonyms. Okay, so what did I use as my initial guess? So I figured that this happened. So here was the reason I guessed this. So this point right there where the natural log graph intersects the x-axis is the point 1, 0, right? So I said, okay, well, my initial guess is going to be x1 equals 0.5. If they don't tell you where to start, you can start wherever you want, but if you start too far away, this method won't work. So just be careful that you really do pick it kind of close to the 0 that you're looking for. And then x2 is x1 minus h of x1 over h prime of x1. Hey, what is h prime, by the way? 1 over x plus 1. Great. And so for x2, I got 0.577258872, just in case you want all those digits. For x3, that's x2 minus h of x2 over h prime of x2, and I got 0.565224492.
I can't plug in quick enough.
It's okay. It's all right. And then for x4, which is x3 minus h of x3 over h prime of x3.
Do you want us to write the formula every time?
No, I'm just doing it to be like super conservative. 0.567. I don't know why I stopped there because I really shouldn't have. 141214. Oh, I didn't. I stopped at x5. So far, how many decimals do we have matching? 2. And if you were to subtract these, is the difference going to be less than 0.001? It'll be close, but not quite, right? So since you're probably close, maybe one more iteration would do it. x5 I found to be 0.5671439. So in that iteration, I got even more accuracy than I needed, so that's the one I go with. WebAssign will tell you how many decimals to round to in this section. It's often quite a lot. Okay? So the thing to be really aware of when you're doing this homework is you have to use that answer feature in your calculator, because otherwise you're going to be typing in so many numbers, it's going to be super tedious. I'm actually not going to give a quiz on this. I'm just going to do the homework because I have to teach it, but I'm not going to give a quiz on it. The quiz will just have section 4.9 in it. Yeah, and there will be a quiz that you will get a calculator on for sure, just not this one. Okay. All right, now this one, how might you find the 6th root of 2 correct to 8 decimal places? So how could you translate that into a function? If you don't know something, you could make it a variable, right?
2 to the 1/6.
Yeah, so 2 to the 1/6, let's let that equal x. Does that make sense? As a simpler equation, isn't it easier to say that's the same thing as saying x to the 6th equals 2? Does that make sense? Or how would you make that an equation that's related to 0 now?
X6 minus 2 equals 0.
X to the 6th minus 2 equals 0. And so that tells you that the function you're going to use is x to the 6th minus 2. Finding where that 0 is the same as finding the 6th root of 2. So this point, this example, kind of like the last one, is like, how do you translate this into an equation? Once you've got the equation, you can use Newton's method to figure it out. Yes?
Are there gonna be problems problems where we have to figure out an equation, or is it just gonna be a lot like these ones where we already know how to get it?
Oh, they'll be awfully similar.
Okay.
Yeah, they'll be quite similar. Okay, so we have this function, and for my x1, I just chose x1 to be 1. I mean, I know 1 to the 6th isn't 2, but, you know, it's pretty close. 1 is awfully close to 2, relatively speaking. Okay, and here's what I got for, I'll just lead you through what I got. x2, I got 1.1, 1, 2, 3, 4, 5, 5 6s and a 7. Sorry, that wasn't very clear. I'm just saying. Yeah, you're like by 1, 2, 3. Yeah, I'm sorry. I couldn't both count and speak. I'm terrible. So for x3, I got 1.12644,368. So I have just one decimal matching. You're like, oh my God, it's going to take forever. But then x4, you have hope. I got 1.12249,709.
Is there a point where you're like, it's too far away, so you change it?
If it's too far away, it's going to be pretty obvious that it's not going to one spot. We'll have an example of that, okay?
Is it generally always 4 to 5 times?
This one took 6, but yes. And it would have been better if I would have had a better guess. If I would have guessed like 1.1, it might have went faster. For x5, I ended up getting 1.12246,205. So I think then I have 4 decimals matching. And for x6, I got the same thing as x5. 1.12246,205. So there's your thing, correct 8 decimal places. Isn't that, you know, a calculator would give you the exact same thing, right? This is just how that calculator is working.
Yeah, because technically it can't be the same, right?
Well, no, technically, I mean, this is an estimation, but you never, yeah, the exact answer is the 6th root of 2, right? I mean, and how much accuracy you need will affect how many iterations you must do. But that, for all intents and purposes, that might be good enough.
Irrational number, no calculator would give you the exact answer.
Exactly, yeah, not as a decimal, because the exact answer is the 6th root of 2, right? There's no repeating decimal that gives, it's what irrational number is. And approximations, yeah, says the students who are always like, decimals, all the way. Not all of you, but you know, it's. Okay, so here is where Newton's method will fail. And it's because your initial guess is too far away. So let's just look and see what happens in this case. Okay, so we have x1 equals 2. x2 is x1 minus f of x1 over f prime of x1. F prime of x1 is going to equal negative 3x squared plus 12x minus 10. I'm pretty sure that when you do this, so 2 minus, that's going to be negative 8 plus 24 minus 20 plus 6 divided by negative 12 plus 24 minus 10. So this adds to 4. This adds to negative 2, right? So that's 2 divided by, what's this? 2, I think, right?
Mm-hmm.
Yeah, so that's equal to, x2 is equal to 1, okay? I know it's arithmetic. But negative 12 and negative 10 add to minus 22, and then plus 24 makes 2, right? Okay, so yeah, okay, so we believe x2 is 1. And you're like, wow, whole number, awesome. That's what I felt like the first time. And then let's go find x3. So x3 will be 1 minus -1 plus 6 minus 10 plus 6 divided by -3 plus 12 minus 10. Okay, what does this bit add up to? I think so. I was just checking that I was right. 1 divided by, and the second bit adds up to, almost, I think it ends with -1.
Yeah.
So that's gonna be, x3 is gonna be 2. And so now to find x4, you do x3 minus f of x3 over f prime of x3, right? Which is the exact same thing we did right here, isn't it? So that's gonna give you 1.
Does it keep repeating like that?
It's gonna flip-flop, yeah. So first you're gonna, so it's, the point is, it's obviously not gonna converge.
Is that because the initial guess was wrong?
The initial guess was too far away.
They
And
gave
so,
us to this on purpose.
yeah, they gave it to you this on purpose, and I'm gonna show you this would happen. So what might happen if your initial guess isn't right is your answers, they're not necessarily all gonna oscillate. This one was like pretty nice that it oscillated back and forth exactly. But when they don't appear to be going to a number, like when the limit is not converging. Well, no decimals is not irrelevant. It could have gone like 2, 1.7, 2.3, 1.9. I mean, like maybe it didn't appear to be going one particular place. This one is really odd, but the point is your initial guess has to be sort of close enough. And the picture looks a little bit like this. Like the y, it fails. This is where the x1 was. And the 0 is way the heck over here. And so when you find the tangent line here, it gets you that number. And then the tangent line at this point gets you this number. And so it ended up going like, or no, I think it must have been even over here. So it then gave you back this number. So it just kept going back and forth between those numbers. So this number you guess has to kind of be over that hump on this side for it to converge to the right spot.
So how do we make a good guess?
You pick something on the sort of same side as the 0 and around any curves or bends.
So we should graph that.
Yeah, you should graph that function. So you should graph the function and just say, okay, well, this is my 0. I mean, if I zoom in, it appears that that's like 0.5. That'll be my guess. And sometimes to make the answers be consistent, they'll tell you what to guess. But yeah, you should graph the function and see about where does it cross the x-axis. Just zoom in and make an initial guess. So.
Is there an online program?
Yeah, there are online graphing calculators you can use. Do you have a Mac? No, okay. Because the Macs also have like a graphing app on the computer that's standard. It's called Grapher and it's really nice. But if you just Google online graphing calculator, you'll find something.
My favorite is Desmos.
Oh, I've heard good things about that. Yeah,
Yeah, that's pretty.
that one's pretty good. I think I actually have used that one. I just use my graphing app on my Mac. I almost never use anything online, so.
Wolfram graphs too.
Yeah, Wolfram graphs too. Yep. If you just say graph blah, it will do that for
Desmos
you.
is better than Wolfram for graphing.
Okay. I'll go check them out. All right, so Newton's method will also fail if your derivative is 0 anywhere in your sequence. And that's pretty easy to figure out why, because the formula was this. xn plus 1 is xn minus f of xn over f prime of xn. And if your derivative is 0, well, that's going to create some problems, right? So that might involve picking a different initial guess or something like that. But the point is, if your derivative is 0 anywhere in the sequence of values that you get, for whatever reason, that's no good.
If we took our original function and solved for y, would that give us a good guessing point?
Most of them you won't be able to, you're going to want to find where y is 0, and most of them won't have any other method to get a guessing point. All right, now this function is not differentiable at x equals 0. Who remembers why? What's wrong with x cubed at x equals 0? It's a vertical tangent line. And it's pretty easy now that you know derivative formulas to sort of show you that that's the case, because f prime of x is 1/3 x to the negative 2/3, right? Which is the same thing as 1/3x to the 2/3, and it's pretty obvious you cannot plug 0 into that denominator, right? But you could with the original function. And it's not a corner, obviously, and the function is continuous. It's that whole vertical tangent line thing going on. As you get close to 0, your tangent lines have slopes that approach infinity. And if you were to graph this function, you would have a function that has an asymptote at 0. Okay, so show that Newton's method fails to converge using x1 equals 0.1. Okay, so if x1 equals 0.1, x2 will equal x1 minus f of x1 over f prime of x1. When you work this out, you get negative 0.2. When you do x3, you get negative 0.4. When you find x4, you get negative 0.8. What do you think happens when you find x5?
-1.
You get negative 1.6. You said that every time you repeat this process, your answer is multiplying by 2, right? So do these numbers appear to go to a specific value? No. So these numbers keep increasing. Or, well, decreasing, I guess. And it fails to converge. And the reason is that f was not differentiable at x equals 0. So you couldn't apply Newton's method near that point. So the conditions are the function has to be continuous and differentiable. So if it's not, you can't, at least not near that value, you can't apply it.
So anytime that function difference into a fraction, we have problems.
If it differentiates into a ratio and the function is not defined at that 0, then the function's derivative is not defined at the 0, then it would create a problem, yes. But we also had a function where we differentiated natural log of x, and we got 1 over x, and that wasn't an issue. So it isn't always going to be an issue if you have a denominator. It's just that if the function isn't differentiable, then there'll be a problem. Okay, so that's it for this lesson.